Okay, as per your statement, we were finished with this slide, efficiency of algorithms, huh? And now we are going to start uh, the topic of asymptotic notations. If I will show you here, CLO 1.1 describe fundamentals, concept of algorithm, design analysis, and these are the topics: asymptotic notations, complexity measures, and correctness proofs. I have to cover these topics at least in this CL. So now this is that asymptotic notations. We want to analyze the algorithms. And if we want to analyze the algorithms, we can analyze them theoretically, mathematically, by using some asymptotic notations. And those asymptotic notations are generally three asymptotic notations. First one is big O, second one is big omega or theta. The little o and the little omega is also existing, but you will see what is the difference between big O and little o. Through these asymptotic notations, we can analyze the feasibility of algorithm. What it means that the algorithm is uh, okay for us or not, correct for us or not. Feasibility normally is some process to check something that is good to go or not, huh? Normally it means it is good to opt that direction or not, huh? So there are three asymptotic notations: big O and respective little o, big omega, so respective little omega, theta. So big O is normally linked with the upper bound. What is upper bound? We will see in the next slide. What is the definition for this? Omega is linked with the lower bound, and theta is linked. And as far as these worst case, best case, and average case is concerned, these are the three cases of complexity. We will see what is complexity and how we can calculate the complexity. We will see. But big O is normally used to represent mostly worst cases. Okay. Generally, big O is used when big O and something is written, then it means it is for the worst case of that algorithm and representing only upper bound. And if big omega and something is written within parentheses, then it means it is for the lower bound only, and it is representing the best case of the algorithm. Best case means where the algorithm is taking the minimum number of operations. Worst case is maximum number of operations. Average case is in the middle. Huh? So now, if we have a problem, we can find different solutions for that problem, and then we can analyze those solutions individually, separately. And if those solutions, you will calculate, after analysis, you will calculate the worst case for each solution, huh? By using big O. Huh? And then the solution which will have the optimal worst case, best possible worst case. If you have four solutions and you have analyzed all the solutions with the big O, which means for the worst cases, and which solution has the minimum big O, that is the optimal. Huh? That is the yeah, less sports. No, less worse. Less worse, yes. Less worse, yes. So is said to be optimal. So what is optimal? From these 4, 5 solutions, the solution which is taking minimum number of operations, less worse, you can say. So, and then we will select that, and that would be efficient. Okay, we will take that optimal, and that would be efficient. This is how these asymptotic notations can help us. But we use asymptotic notations only for judging or for calculating the worst case or the best case or the uh, average case mathematically, theoretically and mathematically. Now we are starting with the big O. We know that this big O is for the upper bound. Generally, short for your understanding, what is mean by upper bound? You will calculate something with respect to big of O, with respect of big O, you will calculate something. And if that thing would be less than or anyhow, suppose once again, suppose you will calculate something like that about the algorithm, some value. And you, when it is saying big O and upper bound, it means that the number of operations would be either equal or less than this upper bound or upper value. If I'm saying that this is that value, you calculate it. And if somebody is saying that the upper bound for this algorithm is this block, then the number of operations in this block would be less than or equal to this value in this block. This is what it means. So first, big O is representing worst case time complexity. Worst case time, we already know from the previous slide that it is for the worst case. It is the upper bound. Now, theoretical definition and then mathematical definition. We say that a function f of n is order of g of n. When we can say this? Theoretically, function f of n is order of g of n. We can say that this f of n is big O of g of n, okay? Normally, big O is called order. In speed, it is called order of g of n. So in other words, we can say that this, if algorithm, you will calculate this, this has this worst case complexity, theoretically, yeah? What it means, what this means, it means that f of n, if it is less than or equal to this, and then you can say this f of n is here, f of n is here, and g of n is here on, and then less than or equal to, okay, remove this. So less than or equal to f of n less than or equal to g of n. This is the picture now. What is the meaning of this f of n is order of g of n? Means f of n will not greater than this g of n. Simply, or how you can say, will not grow faster than a certain multiple of another function, g of n, will not grow faster than g of n. You can also say like that. Once the input size is large enough, this function is a function for the algorithm, and the size of the normally algorithm will take input. It will start from the minimum, and you will keep it increasing the input. And when the input will reach at the largest level, then it would be, you can say, it would be equal or it would be equal or less than. So value of f of n will be what? Equal or less than. Generally, it means it would not be greater than g of n. Just wait. And then I will start with this second point. Just wait for this ending of Adhan, and then we will start. Okay. So we were here. A function f of n, we can call it order of g of n. But what it means that f of n will not be higher than g of n. But we are saying f of n will not grow faster than a certain multiple of another g of n. Here, certain multiple means something will multiply with this g of n, okay? And that thing would be constant c, as you can see here. Cgn, huh? In the next equation, this c is now the multiple of this g of n. And then f of n is always what? Less than or equal to cgn. This is the equation, which is the same equation. And I'm just explaining this multiple of another. So now you have the understanding of this. That is theoretically. Now, mathematically, we can call that f of n is order of g of n. Again, the same thing. F of n is order of g of n. How we can say that this f of n would be order of g of n, which means that this will become the time complexity of this function, huh? This is another reading, huh? So you have to do what? If there exists, you have to find a positive integer and a constant. So here you can say if there exists a value of positive integer n, so you have to find some positive integer which you can call it n0 from the input. From the input, you have to find if there exists some value and that value is a positive integer n, and you will call it n0. N0 is the starting number. And then there is a positive constant c. You will find that. And after that, f of n would be less than or equal to cgn. And if this condition holds, and if this inequality, we call it inequality. When you have equal and also other less than there, we call it inequality. If this inequality holds mean it will become true, that this f of n, this running time will always be less or equal to this g of n. For all n means positive, for all positive numbers, greater than this initial point that you have taken. If for all n, and n, whatever the number you will take greater than or equal to n0, if this equation holds, only then you can say that f of n is equal to order of g of n. Have you the understanding of this statement mathematically? What this statement is saying, huh? Anybody who has not the understanding of it yet? What I am saying that I can call it that this function would be big O of g of n or order of g of n only then when I find two things: some initial points from the size of the input n0, and I will find some positive constant c, and I will put this in this equation, and then the value of f of n, you will see next, the value of this f of n will be always less or equal to this cgn for all positive integers. And this equation holds, then I can say this order of g of n, then I can say, then this f of n is what? Now f of n is what? Big O of g of n. You will get some equations for f of n. In mathematics, you will have some equations for f of n and some equations for g of n. And then the question can be, can I say f of n is order of g of n? And then you have to calculate this. And if you will be successful in getting that, then you can say f of n is order of g of n. And this is what? And this f of n is less than g of n, which means that g of n is always higher. And here, this is a graph. It is showing that this is n, this x-axis is n, and representing input of your algorithm, of your function, and which is this input size, this input size, this input size. Before that, before n, here you are finding something for n0, which is we are talking here. And before that, sometime f of n was becoming higher, and sometime gn was becoming higher. Huh? It was a mix. But now, when you find this n0, after that, gn is always higher, and f of n is always less than or equal. Huh? Here it is equal and then lower. And then this mathematical equation is holding. It is becoming true. Huh? And when this is the situation, then you can say that our f of n is order of g of n. Function g of n is always upper bound of this function. G of n is always upper bound. Now, moving next. And we are going to get an understanding through example. Let's try it. So 5n square minus n plus 1 is equal to order of n square, if it is given there. And then this is our f of n. And here, big O, and then this n square is our what? G of n, according to the notation that we studied in the previous slide. So f of n and g of n. Now, what we have to prove? That f of n is less than or equal to cgn. And for this, we have to find n0, initial point, and then we have to find positive c. And then we will start putting in the equation and see for different values. So according to that previous definition, we have to find c and we have to find n0. And then we have to prove this equation, f of n less than cgn for all n greater than or equal to n0. And here we are doing that. 5n square minus n plus 1, this is f of n. And then this n square is what? This is g of n. And this is the equation, f of n less than or equal to cgn. And here c multiplied by n square is what? G of n. So this is cgn, huh? And then here it is n, and we are starting it from 0. See, 0 to onward. You don't have to take too many values. Just check 4 or 5 different values and then say, okay, this is true, and then move on. Huh? just to get the understanding about this big O, when we can say that the f of n is normally, what is f of n? It is the running time of your algorithm. And then you are going, then you want to say that the running time, worst case running time of my algorithm is order of g of n. So anyhow, so this is your f of n, and this is your n square is g of n. So it is becoming what? It is becoming cgn. And this is your f of n, and this is your cgn. Now n is equal to 0. If I will put 0 here, so there is no specific or fixed method through which you can calculate what is the value for c. Okay, what is the value for c? There is no fixed method. For n0 it is fixed, you can see, but for c you cannot. But there is a hint, and that hint is you have to check what is the maximum number in the, for this is n square. N square is this. What is the maximum digit for n square? Coefficient 5. And then you have to check from 0 up to 5 these numbers, and then you will find something in between. This is not always correct, but it is most of the time it is correct. So n is equal to 0. And then if you will put n is equal to 0, this becomes 0, this becomes 0, and then you will have only 1 here. And then here, if you will put n is equal to 0, this whole, whatever the value of c is, it will become 0. And then what is happening here? F of n is greater than 0. And we have to prove f of n is less than or equal to. It is opposite. It is opposite. We have not finalized our c yet. Okay, then if so here, if I will put c is equal to 0, it is also okay. I'm just going next. N is equal to 0. So now if I will put 1, then it will become what? 5 minus 1, 4, 5. So minus 1 and plus 1 is cancelled, and you have 5. Minus 1 and plus 1 will be cancelled, and you have only 5. Understood? And then here, if n is 1, so 1, 1 square. And what is c? If you will take 0, it will become 0. And then 5 greater than 0, still greater. I want to make it less. So then take 1 or 2 attempts and then change the value. So then change the value of c, this 1. If I will make it 1, then what will happen? So for 1, 1 and 1, 1, I will have 1 here. And 5 greater than 1 again. I don't want greater, I want less or equal. So then quickly check 2. If I will make it 2, for this one, 2 into 1, it will become 2. And here I will have 5. 5 greater than 2 still. I am checking here because it is 1. I don't have to think too much. Here I am checking what is the right constant. Okay. And if I will put 3 here for the C, here I have 5. And but for n, it will be 1, 3 and 1, and I will have 3 here. For 4, 5 greater than 4. If I will take 5, 5 equal to 5. So for a moment, I will stop at here that my C would be 5. So if my C is 5, then this would be 5, and this would be 5, and 5 equal to 5. Okay, equal. Now check next. If I will take n is equal to 2, this is your input size. And then n is equal to 2, so 2, 2, 4, 4, 5, 20, and 20 minus 2, 18 plus 1, 19, and you have here. And then if n is 2, 2, 2, 4, 4, and 5, 20, and 19 less than 20, this is what I want. This is what I want, this is what I want. So for 2, it is okay. Now check for 3. If for 3, you have this 43 here and 45 here, it is again less. If you will put 4 in this equation, you have 77 here, and it is 80 here with C is equal to 5, okay? And it is less. And in this way, you are getting less values. And now you can consider your constant is 5. If there is some other constant is possible, okay, possible, but this is also possible. So this table is showing that we are going to get C is equal to 5. Okay. Through this table is giving you an idea that we are going to get the value for C as 5. And what is the initial value? This theory is less than or equal. And the equal, I have equal status here. And then initial value for n is what? 1, which is my n0. The first less than or equal. If I will not get this equal, and then this would be my 1. Then this would be my n0. Okay. Understanding? Understanding? I'm asking him. Inshallah. So here n0, here my n0 is now this, and my C is 5. Okay. Now, if you will draw a graph for this table, where this is f of n and this is g of n with these values, if you will draw a graph, you will get this graph like that. This is your input size, input, and then this is your n0, which is 1. This is your 1, where these two are equal, f of n and g of n. Where f of n, this blue one is now g of n, this red one is f of n. And f of n is always less than or equal to after this point. After this point, it is f of n is always less than or equal to cg of n. And before that, opposite is possible. Huh? Before that, here f of n is larger and g of n is lower. Huh? But after this n0, this is your n0. And with that constant, now this situation is changed. G of n is higher, and f of n is always equal or less. So if for this constant C, which is equal to 5, and n0, which is equal to 1 in the table, n0, and n0 is your that point where you are meeting the minimum condition. Huh? F of n, the equation is f of n less than or equal to. So the minimum condition is equal or less. Huh? Or you can say minimum condition is always less and equal is the highest. Huh? F of n, the value of f of n will always be lesser values. And it can keep on increasing, and it can keep on increasing, and it will reach at the equality. That would be the highest point, upper bound, not more than that. So for this C and for this n is equal to 0, now 5n square, which is f of n, is always less than or equal to Cn square, which is Cg of n. Which is, and n square is what? G of n. We have assumed it here. This is G of n, this is f of n from the question. And now, such that this equation for all values of n greater than, n is what? N greater than or equal to n0. N is what? When your n values are greater than or equal to n0. This is n0. And then values are greater than or equal. Huh? And then this condition will hold. And in this way, it is proved that this 5n square minus n plus 1 is what? It is order of n square. I can write it. Now, then you can write it that this 5n square minus n plus 1 is what? It is order of n square. Another meaning. Now, theoretical meaning. Now, it means that for this, when we normally calculate running times of different operations involved in algorithm, then you will get something like that. 5n square minus n plus 1. You will add different operations. You will add timing of the different statements involved in the algorithm. And suppose this is a running time of one statement, this is running time of another one, this is constant running time of another one, and you are adding them. And then you will do what? The shortest method is ignore lower terms and keep only the higher terms. And then you will ignore lower terms, and this is only the higher term, 5n square. And then you will ignore again the coefficient, and then finally n square will remain. And then you can represent order of n square. Short way. But this is actual understanding. This is actual understanding. You are checking the size of the input on the data. And what is the size of the input? Here the size of the input is 0. Here the size of the input is 1. Maybe 1 element, 2 element, 3 element, 4 element, 5 element. How many of you have the understanding of this mathematical example in which we have proved f of n is less than or equal to Cg of n? 1, 2. Honestly, because we don't have too much people, huh? What about you? And no understanding. Ghazi and you, what is happening with you? Okay, these examples are coming again and again. First, big O is finished, and now big omega will come, and then big theta will come. So you have 3 attempts, and I hope you will understand. Huh? But this here, take it as a mathematical question, and then you will understand. Huh? Now, big omega. What is big omega? Big O is for the worst case, and big omega is for the opposite, for the best case. Worst case, maximum number of operations. Best case, minimum number of operations. And the third one is what? For the middle, for the average case, which will come next. That is theta. Big omega. How we can write? We can write it like that, big omega. Represents lower bound. Previous was f of n less than or equal to Cgn. Previous equation was f of n less than or equal to Cgn. And here it is opposite. So then condition will change. F of n greater than or equal to Cgn. Okay. Good. So the first thing is this big omega we will use this notation for representing best case time complexity. If you are going to represent worst case complexity of your algorithm, then you have to use big O. And if you are going to represent best case of your algorithm, which means minimum number of operations, then you have to represent what? And then you have to use what? Big omega. And then if you are going to represent average case, not worst, not best, actual, real average case, then you have to use theta. Anyhow, this omega, it will measure what? It will measure the best case time complexity. Best case running time, you can say. And we can say that f of n would be equal to omega g of n. What it means? Here, f of n means running time of your algorithm. And then you are saying that running time of my algorithm is omega g of n, which means best case of my algorithm is g of n. Omega is for the best. Now we want to say that the running time of our algorithm is omega g of n. How you can represent it mathematically? Like this. F of n is equal to omega g of n. Okay. Ghazi, once again. The running time, I'm saying a sentence. The running time of my algorithm is omega g of n. This is a sentence. I can write it on the whiteboard. Huh? I can write it on the whiteboard. How I can say it in mathematics so that I don't have to use words? This is the way. If I will write f of n equal to omega g of n, mathematicians will understand what is this. So being a algorithmic student, we can understand that here what we are saying, f of n, which is the running time of our algorithm, is omega g of n. This is what we want to say. And when this will be, if we will find some constant c and also a value n0, the same definition, and also a value n0 for the inputs, for the inputs of n, for all the inputs of n, for which this f of n would be greater than or equal to cg of n. This is exactly the opposite of that previous big O. Okay. And what it means now, this is written mathematically, but what it theoretically means in words? It means running time of my algorithm is always higher or equal to this running time which I calculated, which whatever it is, or running time of my algorithm is always greater than or equal to g of n, simply. When it is the situation, I can draw that graph again. So this is for the input, and I have to find n0 similarly as you have done previously. Before that, anything can happen. Sometime that would be higher, sometime another can be higher. But after that n0, if this condition holds, f of n is always higher than cg of n. This is what, and if this condition will hold, only then I can say f of n is equal to omega g of n, otherwise not. Only then I can say that the running time of my algorithm is the best case running time of my algorithm. This is what it means. Omega, best case running time. In other words, this is what I'm saying. In other words, I can, anyhow. And when f of n is higher and g of n is lower, then it means that this g of n is always lower bound of the function f. Lower bound, at a lower bound, at a lower boundary. From the boundary, we have a bound. But after a certain value of n, but when we find some value from the n, like n0, then f will never go below the g of n, which is written here. This is written in a graphical way, and this is written in words, theoretically, nothing else. Now moving towards the example. If f of n is equal to 5n square minus 3 and minus 3, and we are saying that this running time is equal to n square, and we are saying that this n square is the best case running time. And how we can say? By omega. And then this would be what? We are calling it g of n. We are calling it g of n. And now we want to prove this thing, f of n greater than or equal to cgn. I can say this thing in a different way, but I don't want to make you confused. When I will say two different things, too many things, then it can become a reason that it will make you confused. So that's why I'm trying to give you only one explanation. So f of n, now this is my f of n, this is my g of n, and it is equal. I have to show that equal here according to this equation. Otherwise, how I can show that? When mathematically, according to its definition, when I will show this condition is holding after n0. So according to that previous theory, according to this definition of big omega, I have to show that for some positive constant c, And for some initial value n0, f of n would be always greater or equal to this CG of n, where n would be what? These for all n, and n would be what? Positive numbers from 0 to onwards. And these would be higher than n0, your selected starting value. And for this, by using the same method, if we will take c is equal to 4, okay, and how I extracted 4, you know that from 0 to 5, you have to do hit and try, and then you will find, and then you will find where this condition is becoming true, where this condition is becoming true. So suppose we are taking c is equal to this 4, and then for 1, here I will get 1. And here put 1, and the value of c, you will get 4. So 1 is less than 4, okay? Now for 2, from this, after putting n is equal to 2, I will get 15. And after putting n is equal to 2 here and c is equal to 4, I will get 16. So f of n is less than 16, opposite of this condition. Okay, moving next for 3, when you will put this 3 here, you will get 39. And you will put 3 here and c is 4, you will get 36. And 39 is greater than 36. Now, okay. So now this condition is true. Now this condition is true for 3 when your number is, and also for the next, when you will get 4, it is 73, and here 64, and it is greater. And next the theory is true, and next the equation is true, okay? For next numbers, for all positive numbers greater than n0. What is then n0? This is n0. Equal is not existing, but less than. The first greater than from where it is starting. So then your n0 is what? There, and your n0 is what? 3. And for all the n's, and all the n's are greater, all the n's greater than n0. And this is that direction. And your equation is then true. This equation is then true after 3 and all n's after 3. And your 3 is what? N0. How many have now the understanding up to this point?